Hi everyone. In this video, we're going to look at bootstrapping and Monte Carlo simulations with R. So we're going to talk about Monte Carlo methods very generally, some fundamental uses of these in R. Monte Carlo, in some sense, is a fancy word for random. So it's kind of like random methods or randomization methods. It's ways we can use simulated data to answer questions of interest. Okay. We'll also look at bootstrap methods and what that means exactly. There's sort of many different types of the bootstrap. The most common being what's called the non-parametric bootstrap, which is actually so common that it's just often referred to as bootstrapping. But when people say that, they're commonly referring to the non-parametric bootstrap. And then we'll talk about the less common, although still used somewhat, parametric bootstrap, which is very similar, sort of a slight variation of the original bootstrap approach. Okay. So we'll talk about these things very generally, these three things. And just like usual, we'll get started making sure we can load these packages and install them if need be. Okay. There might be some new packages here this time for you. The ggdist package, which we will use to create rain cloud plots. Okay, so those are a little bit of a fun extension of the box plot or a distribution plot. Okay. Let's see an actual example of one here. Rain cloud plots. There we go. So the rain cloud plot, not this one quite here. Right here. Here's an example of a rain cloud plot, or specifically this one here. Okay, so you have like a curve showing the density of the values, a box plot of those same values, and then a dot plot, technically, all aligned with each other. And collectively, this is become referred to as a rain cloud plot because these kind of look like clouds with the raindrops underneath. Kind of a cutesy little take on a extension of a box plot. So we'll take a look at those, and then we'll also use the broom package just to tidy up some output from fitting or using a two-sample t-test in R. So the broom package is a package made by the tidyverse developers, or people contributing to the tidyverse who wanted to simplify the process of displaying output from models fit in R, like output from the two-sample t-test, an ANOVA model, a regression model. They wrote this package to be able to get output from that in a nice, tidy format. So like a Tibble, a data set with rows and columns containing like the model coefficients, p-values for each predictor, standard errors for each predictor, all of those as different columns in a data set. Okay, so that's what the broom package is useful for. Okay, so we'll get those packages loaded to start. Okay. You may need to do install.packages and run that in the console. Remember, you don't want to run install.packages inside chunks in an R Markdown document because that gets rerun every time you knit your document. You just want to run it once in the console typically for install.packages. Library command we want to rerun every single time, so we'll put that in an R chunk. Okay. And sometimes if you try to load a package that you don't have installed, R will give a nice little prompt up here that you can just click on a button that says install and it'll do it for you. That works great too. So Monte Carlo methods in R. So as I mentioned earlier, Monte Carlo, in my view, is somewhat just of a fancy term for random or simulation methods. Okay. So Monte Carlo methods are a wide class of algorithms that use random sampling or simulation of values, simulating values to solve probability-related problems or just other difficult optimization or mathematical questions that may be of interest. So for example, starting with a simple problem that we certainly don't need simulations or Monte Carlo methods to answer, but we'll talk about how we could. We could consider the situation in which we're rolling a six-sided die, a fair six-sided die. So each side of the die has an equal chance of showing up. In that case, what's the probability or chance that we roll a 6 on a single roll? Okay, we know because it's a fair six-sided die, 6 is one of number, so there's a 1 in 6, which is about 16.7% chance that we roll a 6. Okay, we know that, and we can express that mathematically. So there's no need for simulating many dice rolls to estimate this probability. What about a slightly different or slightly more difficult question? What's the chance of rolling 2 6s in a row? Okay. So in that case, we still might know the answer. Okay, if they're independent die rolls, we can take 1/6 times 1/6, and that would give us the chance of rolling 2 6s in a row, about just short of 3%, okay? Or 1/36 if we want to be exact. Okay. Again, probably don't need to simulate dice rolls or using Monte Carlo methods to approximate this probability, since we can express it exactly. But we could consider more complicated scenarios. What are the chances you roll 3 6s and then 2 4s and then a 3? Again, we could do that mathematically, but it starts to get more difficult. What are the chances that you roll 3 of any given number, 3 of the same number, 3 times in a row, and then 2 of a different number in a row? Questions like that might start to get more difficult. We could still get to it mathematically at some point, but we could estimate these probabilities with actually a high degree of certainty by simulating dice rolls using our coding skills. Okay. So let's look at this situation of simulating a single dice roll. Okay. The sample function in R allows us to randomly select elements of a vector. So we could use this to emulate or simulate the rolling of a fair six-sided die. Using this code here, we can simulate the roll, a single roll of a fair six-sided die. We can run that. We got a 2 again, and then a 5 again, 4 again. Oh my gosh, we keep getting the same numbers. Okay. So you likely don't see the same numbers as me if you are trying to roll your dice. And that is expected. That's not surprising. This is a random generation of a value from this vector 1 through 6. Okay. And we're saying we want one number picked from that vector randomly. Okay. So you don't get the same result necessarily each time you randomly select it. So very generally, the sample function allows us to randomly select size number of values from a vector. And if you have more than one value, so we could simulate, say, 2 rolls of a dice. And we can do it like this. And then we get 2 rolls. But this isn't actually correct how this is being done, because if you keep rolling, you'll see you never get the same 2 numbers in a single 2 rolls. That's because if you look at the default for the sample function, if you look at the help file, replace equals false. So it's sampling without replacement. We want to be able to, in this case, because we're simulating a die roll, we want to be able to sample with replacement because we want to be able to get the same number potentially. So if you roll, you could keep rolling, and eventually we get the same number twice in a row now that we have the option replaces true. So depending on what you're wanting to randomly select, sometimes you want replace to sample with replacement, and sometimes you want to sample without replacement. It depends on what you're going for. So in this case, with a dice roll, we want to sample with replacement. Okay. All right. So let's simulate 100,000 dice rolls, 100,000 die rolls. R is actually remarkably fast at this. It's pretty amazing. You would think 100,000, oh, that's pretty big. And let's store it in a vector called rolls. We'll say instead of 200,000. Make sure you have the right number of zeros here. And R does it nearly instantly. It has all the rolls up here. Okay, you could print it to the console if you wanted. It's a lot of numbers. Okay, look at all those rolls. So instead of mathematically deriving probabilities of certain outcomes or chances of things, we could use the outcome of these 100,000 dice rolls to look at questions of interest. Okay. So one thing we'll look at here are runs of consistent numbers. Okay, so here's a run of length 2, because we have 2 numbers of the same value in a row. So a run of 2 6s right there. Let's see if we can find another run. Here's a run of 2 3s. Ooh, here's a run of 4 4s. Okay, so we could condense. One thing you could do with a vector like this is condense this information into the runs in terms of the value in the run and then the total length of the run. We could use that to condense down this information if we're interested in analyzing patterns in the runs. Okay. So a very useful function for this, we could write some code to manually do this, although it's not easy to do in an efficient way, a way that runs very quickly. There's a function in R, in base R, that's optimized for this using the programming language C, called the RLE function, which stands for run length encoding. So my professor who taught me in my R class showed me this, and it's a really amazing function. He had us write it by hand first, manually, and then it's really hard to get it to run fast, this type of operation, but so we'll call it runs. Actually, maybe we'll stick it in the same chunk. All right, and then we'll do that with the rolls object. Run that. Now we have this runs object. Okay. So here you can see we get like a 4, a single run of 4, a single run of 1, a single run of 6, single run of 1, and then a run of length 2 2s. Okay. So this vector ends up being, well, this has less rows than this object. Although I guess it's a vector, so it doesn't really have rows, it just has elements. But notice that there's only 83,000 rows in here rather than 100,000. Also, what's kind of interesting What do we notice about this number here? What is that roughly equal to? If we think about what we were doing, we were rolling a fair six-sided die. The chance of any given number, 1 in 6. Now let's say we rolled a 6. What's the chance of getting another 6 on our next roll? Well, if they're independent, it's still 1 in 6. But what's the chance that we get any other number besides 6 on the next roll? Well, that's 5 in 6. About 83.3%. This number up here, 83,384. If you divide that by 100,000, you get about 83.3%. And the larger our sample size, the more this would correspond to exactly 83.333 repeating percent. Okay. It's not exactly because of random chance. These are randomly generated numbers, although it's pretty close because our sample size is so large. Okay. So what proportion of rolls for each number? To answer this question, first, let's get the rolls into a tidy format. So let's call it like runs tidy. Okay, so we'll make a tibble, which is like a data frame. And then because this object's just a little bit difficult to work with, like the runs object, you can't like do like a filter. You can't do the dplyr operations directly on it, like filter lengths greater than 2. Like you can't apply dplyr functions to it directly. We have to convert it to this tidy format first, which will look very similar to this. Okay, so we're going to make like tibble like this. Just to make it a little easier to work with. So it looks very similar, but now we can use dplyr operations on this runs tidy. Okay. So let's see, what proportion of rolls for each number? Okay. Think back, what have we seen that we can use? Which dplyr function can we use to get a frequency table for a variable? Oh, and let's actually, before we make the runs tidy, I suppose let's make the rolls tidy as well. So rolls tidy. And then maybe we'll call it like roll. Just so that we can use some dplyr functions on this too. So now we have this rolls tidy, which just has one column. Okay, how can we make a frequency table, a table of counts using a dplyr function? So we can use the count function. We'll say count roll, since roll is our variable. Oops. Let's see. Oh, wrong data set. There, I gotta fix that typo. Here we go. Okay, so how many rolls did we get of each number? And what does this look eerily close to? About 16,600 or so of each number. Again, awfully close to 1/6. We calculated that number times 100,000. All right, so we could approximate these probabilities of each number here. Again, unnecessary for this simple of a problem, but we're showing how we could approximate it using what are called Monte Carlo methods, essentially simulation methods. Okay, now, yeah, using the RLE function, what are the most consecutive rolls with the same die value? Okay, so now we can answer this question by looking at the runs tidy object. Okay. We can also use the count function again, this time on the lengths. So it looks like, ooh, we got one run of 8 numbers in a row. You might not have even gotten that many. I doubt you got more than 8. I have yet, running this a bunch of times, I have yet to see more than 8 numbers in a row. A little surprising to me. Again, thinking about what we're doing, we were rolling a dice 100,000 times. The largest number of times in a row we got the same number, 8. And for you, it might have only been 7, depending on your rolls. Really doesn't feel like that many, given 100,000 rolls. That's a very big number. But that's what we see here. Okay. What is the total number of runs of each length? Okay, so here we can see, using the count function, roughly 69 or 70,000 runs of length 1, 11 or 12,000 runs of length 2, about 2,000 runs of length 3, and so on. What is the ratio of the number of runs of length 2 compared to length 1? Okay, this is where it gets interesting. Maybe think about what this probability will be before looking at the numbers and using that. How many runs of length 2 will there be compared to the number of runs of length 1? Okay, so if we look at this here, let's call this run counts. Okay, and we can still print this table up here. Right. And now we'll say, let's see. So if we print this out, okay. This is the run counts data set. So if we want the runs, so we're accessing the n variable. Here's the number, n gives the number of runs of that length. Okay. So we want the second value of that variable right here. So we're saying in the n column, with the $sign here, we're saying in the n column, get the second value of that variable. It's right here, and then divided by the first value. This is a little bit of what we'd call base R syntax, not tidyverse syntax. There's not a concise and short way to calculate the same ratio. You certainly could do it with tidyverse and dplyr functions, but sometimes I like to use base R syntax because it can be a little bit more concise. I think it's good to know both and to use a blend of both, although generally I try to stick with tidyverse or dplyr based functions. But here, this gives us that ratio of this number to this number, and let's see what that looks like. Looking a little familiar. Okay, what about the number of runs of length 3 compared to length 2? What do we think that'll end up being? So that's this number compared to this number. 3 compared to 2. Ah, looks similar again. And what are these close to? 1/6 keeps showing up. Okay. So you're about 6 times as likely to have a run of length 1 as you are to have a run of length 2. And then similarly, you're about 6 times as likely to have a run of length 2 as you are to have a run of length 3, and so on. Okay. So those 6 outcomes, so the ratios are all close to 1/6, 1/6 here. So just, yeah, a little bit of fun with some dice rolling here. It's kind of fun to simulate a dice roll, especially when you can do it so many times. I think even doing this, so that was 100,000 times, runs nearly instantly. I think if you even do like 1,000,000, so add another 0, still runs pretty dang quick. So you just did 1,000,000 dice rolls there. It's pretty amazing. But yeah, we'll just keep it at 100,000 for now. But yeah, R is remarkably fast. So we saw here how we can sample from a vector of the numbers 1 through 6, okay, which was useful or convenient for emulating or simulating a dice roll. But the sample function can be used very generally for sampling from vectors in R. So let's look at how we can randomly select from this fruit vector that's available when we load the tidyverse package. Specifically, it's from the string R package, which is a part of the tidyverse. Okay. Maybe we'll have a new subsection. Other vectors in R. Okay. Yes, we can have emojis in our comments. It's kind of fun. All right. So yeah, let's randomly select 10 values from this fruit vector. So the fruit vector, first, let's just display that. Weird. I don't know why that gave an error, but it still printed just like wanted. Maybe we'll take that out of there. It doesn't seem to like that. Yeah, if you print it right to the console, it doesn't have a problem with that. So here's this fruit vector that's just a toy vector to play with in the string R package, which we'll get to later in the semester, the string R package. But for now, we're going to use it to randomly select values from it. Okay. So maybe we'll call this like select fruits, the ones we pick. Okay, so we want 10 values, so we do size equals 10. Does it use sampling with or without replacement by default? Oh, it's just fruit. Oh, maybe it doesn't like the let's see, maybe it doesn't like the emojis. Okay, it did not like the emojis. I was wrong. I was wrong. Okay, maybe we'll get rid of those so we don't have problems. Okay. Okay. So here's 10 fruits. Randomly generated again, another 10, another 10. Does it seem like we ever get 2 fruits that are the same? No, we don't. And that's because, as we saw, actually by default, it samples without replacement. So we can't get 2 of the same fruits in a single sample. So it samples without replacement by default. Let's sample 10 fruits with replacement. And let's do that until we Maybe we'll call this like unique fruits because they're the same. Or they're unique. They're not ever the two of the same fruits. Here. Okay, so let's sample until we get a duplicate in here. Let's see, there was our first try with this one now. Oh, yeah, we have to update it. Replace equals true. Do we get any duplicates here? I don't think so. Let's try it again. No. There we go. Purple mangosteen. What a great fruit. No, I'm just kidding. I have no idea what that one is. So yeah, so we can sample and we can get duplicates in the same sample. Sometimes that's desirable, like in the dice roll situation. Just depends on your context. So one thing to point out here, although we can just sort of take it for granted, thinking deeply about what is random sampling? Like, what does it mean to randomly select values from this vector? I would say that's not a trivial question to think about. Ideally, with the dice rolls, for example, if we're randomly selecting from the numbers 1 through 6, we would want an unpredictable pattern of 1s and 6s showing up in the long run as we roll the dice. How to achieve that? If you think about somebody actually coded up this function in R that we use, and they came up with some process or algorithm for generating, quote, random numbers. Nothing, it may be a little bit unsettling, but in reality, nothing is truly random that is generated from a computer program. The developers who made this function did their best to make it as unpredictable a pattern as possible. And they certainly have done far better than I or many other people could have ever done in doing that. But in the end, they still used some type of algorithm or process to generate those numbers. And so there is a way in which those numbers could be predictably generated or produced. If you produce it using some algorithm, there's a way to work backwards from that and predict what number is coming next. So they're not actually truly random numbers, but they try to get them as close to, quote, random as possible. If you're curious about that process of how to create random numbers and how R does it specifically, you can submit this to the console. Okay. And R will talk about, here it talks about different methods of random number generation that R can use. So you can specify like there's different algorithms for doing this that you can specify. There's pros and cons to various ones. Some people put a lot of work into this. For example, a professor who taught this class many years before me at Grand Valley did his dissertation on methods for random number generation. Okay. So you can spend many years working on this stuff. Anyway, just as an aside, or we can just proceed on our merry way, assuming these are actually random numbers, even though it's not actually the case. But that's what I do, so we'll just keep doing that for now. Okay. So yeah, that was one sort of deeper question, sort of related to all this random number generation or Monte Carlo methods. One that has a simpler answer, maybe. How can we get reproducible results when using Monte Carlo methods. In other words, how can we get the same random sample again if we want to replicate a previous result? So in R and across all other programming languages that use random number generation, you can get reproducible results by setting what's called a seed value. So a seed value is like a placeholder for the start of the random number generation process. So if you set a seed value before any type of random number generation or random number selection in R, you can get consistent results by rerunning that same code. Even if you like closed R out, did it again next week, you set the seed value before generating the numbers, you can get the same result. So for example, here we can reproduce these 13 fruits that I got here by setting the seed value to 1989 before we sample them. Okay. So let's do that. So you do set.seed 1989. And you just run that. And then we can actually, I won't even store it because we'll just print it. And we'll make it 13. And this goes all the way from, let's see, 13 values from the fruit vector. We don't want to have replacing, I think. Yeah, we won't do replacement. So let's get rid of replace equals true. 1989. There we go. So we go all the way from this. Oh, wait a second. Okay, there we go. I don't know why it was producing some strange results there. Okay, so if we set the seed value and then sample, we run that in the console, we'll have all these fruits starting with salal berry all the way down to mango. And that's the same result here. And you should be able to get the same exact 13 fruits as well when you set the seed beforehand like this. So the seed function, you can look at the help file for it. It takes pretty much a seed value, that's all you often ever set, which is preferred to be an integer. R will coerce it to an integer if you give a decimal. So you can like do set seed 3.1415. But it'll just coerce it to an integer first, and then I'm not sure how exactly it does it, but and then sets the seed value. So typically people always give a positive integer. So like my favorite, and people commonly programmers will have their favorite, value that they like to do over and over again. I really like to use like 1994. It's kind of fun. You can pick whatever value you like and typically set your seed value to that. So this is something you typically do at like the top of your script. Okay, so like I would do it in my setup chunk typically. And then what's nice is if you do it at the top of your document, you'll get the same random results throughout the whole script starting from that point. Okay, every time I knit now. Because it sort of sets the seed up here, and then from that point onward, we will always get the same number generation, whereas we wouldn't before. So it got a 2 here, 1 and 2 there. Okay, those rolls results. So lolberry all the way down to mango because I reset the seed here. So you still need to set this seed right here. If you want to get the same exact result for the fruits here, you have to reset the seed. Okay. But that's how we can do that. All right. So that was talking about sampling from vectors and random number generation. Another broad area of Monte Carlo methods are simulating data from statistical distributions, from probability distributions. So this will be the most math statty, most mathematical we get here, looking at these types of things. So to talk about the most well-known distribution first, the normal distribution is when values of a variable tend to form this bell curve in terms of their distribution or density. So here, the red maroon line shows the true theoretical density curve for values from a normal distribution. And I plotted a histogram using ggplot underneath that shows the values for, I think, 10,000 values randomly generated from a normal distribution. So you can see how, because the sample size is quite large, they follow the true density curve quite well, but not perfectly. And that's because it's a random sample from a normal distribution. It's not the true population. Okay. So this is values generated from a normal distribution, which can be generated using the rnorm function, which stands for random normal. So that's useful for generating from a normal distribution. There's many other functions for all of, or for many of the common distributions that people work with. So for the t-distribution, which you may be familiar with from the t-test, there's an rt function. Chi-squared, there's an r chi-squared function. The exponential distribution, which is useful for many aspects, one of which is for modeling time between events. The Weibull distribution is another distribution that's used commonly for modeling time to event. The exponential distribution, and you would learn much more about these if you took a mathematical statistics class, which is kind of fun. But the exponential distribution, values from it, if you, let's see, like we could simulate, okay, 10,000 values from an exponential distribution, and then plot a histogram. Okay. Let's add a little bit of outline color to this. Okay. Just so we can see the bars a little bit better. Okay, so here's like values from an exponential distribution. Exponential values are always 0 or greater. So that's why it can be useful for modeling time to event, the amount of time until something happens. The exponential distribution relies on an assumption that the probability of the event occurring at any time is constant. And so what that means is if it's been 2 seconds and the event still hasn't occurred, it's just as likely to occur now as it was 1 second ago. Okay, so it has a constant failure rate, or a constant hazard rate, we would say. This makes it not ideal for modeling things like time to a part breaking. So like engineers like to use distributions to model time to something breaking is a common example. So the Weibull distribution is more useful than the exponential in that context, because if a part on, say, like a car has not broken for 10 years, it's getting more likely that it'll break. As it gets older, it does not have a constant chance of malfunctioning. It becomes more and more likely across time that it will fail. And so the Weibull distribution is sort of a generalization or extension of the exponential distribution that can allow for the chance of the event occurring, sometimes the event being the part failing. It can allow for that to increase, the chance of that to increase across time as the part has been alive longer. So that's a useful distribution that I know engineers like to use. The F distribution you may have seen before, for example, in the one-way ANOVA, the test statistic under the null follows an F distribution. The beta distribution is an interesting one. That one is, I think it'll ask me for parameters here. Yeah, shape. What's the shape? Let's give it some shapes to keep it happy. Okay. So the beta distribution is bounded between 0 and 1, can be useful in some contexts for modeling probabilities, since probabilities have to be bounded between 0 and 1. So that's another distribution. There's also the uniform distribution, the binomial distribution, and the Poisson distribution. I'm probably not pronouncing that the best. It's Poisson. It's named after a French mathematician. But so binomial and Poisson values are discrete. So for example, yeah, the beta distribution is like decimals, continuous values, but the Poisson distribution generates numbers, whole numbers. Anyways, not to get too far into the weeds with this, but there's many other distributions as well besides these ones that R can generate from randomly. And so it's useful for simulating or trying to artificially create examples to test hypotheses or models that you're wondering about the performance of. For example, like if the values are actually Poisson, and we try to model that with a linear regression model, how does that do? Like, even though the assumption, there's a lot of like normality assumptions related to regression modeling, but what if things are a Poisson distribution? We can see how it still does. Maybe the regression model still does decent. Okay, so Monte Carlo methods are useful in a variety of ways. Whenever we generate data from these distributions, we have to specify not only the number of values we want to generate, n, but also the distribution specific parameters. So for example, the Poisson distribution, we have to specify lambda. Okay. And so if you look at like the Wikipedia page for each of these distributions, that's where it's the most helpful. I think the Wikipedia pages for statistical distributions are really well documented. In particular, if you go to the Wikipedia page for each one, there's always this set of important information on the right-hand side. You can see like the mean is lambda, median, it's this complicated value. Okay. Other characteristics about the distribution can be helpful. Or in R, if you want to see what that distribution takes, you can look at the help file. So for the Poisson distribution, here we can see for the rpois function, we need n and lambda. And for the rnorm function, we need the mean. Well, we need n. We always need n for all of these, the number of values. But then here are the distributional parameters, the mean and the standard deviation. All right. So we could, for example, simulate a large number of values from these distributions in order to estimate specific parameters about them, like the population mean or the median. Okay. Even though this is known for many distributions, like if you look it up on the Wikipedia page, it'll say, here's the variance, here's the mean. Sometimes some parameters are more complicated and it's difficult to mathematically express those. Okay. Or maybe even impossible. So you have to approximate it with Monte Carlo methods sometimes. Okay, so here, for example, we'll look at values that are actually known, but show how we can approximate them using Monte Carlo methods. So we'll generate 100,000 values. Maybe we'll say, let's call it like simulating data from probability distributions. Let's generate, 100,000 values from a standard normal distribution, which means a standard normal means that the mean is 0 and the standard deviation is 1. Okay. So we'll call it like normal values. Or maybe, okay, let's call it like sim data. And then we'll make like a tibble where we have like the value be the column, and that's equal to these generated. Okay, and then it's a standard normal, so it's mean 0, standard deviation of 1. And let's set the seed beforehand right here so we can get a reproducible example every time. You can set it to whatever you want. Okay. So we simulate those values. Okay, here we can see there's 100,000 values generated from a normal. And now we can estimate the median of the standard normal distribution using the quantile function. Okay, so again, you may be wondering, why are we going through all this trouble to estimate the median of the standard normal? Does anyone know what the median of the standard normal is? Mean is 0, and it's a symmetric distribution, so actually the median is the same. So anytime a distribution is symmetric, the mean is equal to the median. So here we can estimate the median using Monte Carlo methods, though, even though we know it truly should be 0. Like this. Okay, so we access those generated values. And then in the quantile function, we have to specify probs, which quantiles we want. When we want the median, that's the 50th percentile. So we make this 0.50. Okay. Let's see, the estimates minus 0.003, pretty close to 0, but not exactly. And that's again because it's a random generation of values. If we did 1,000,000, we'd probably be even closer to 0. Yep, you can see it gets even closer, but we were just doing 100,000. So. Okay, notice we get that reproducible result because we set the seed value. All right, now let's calculate the 97.5th percentile. Okay, we can use those same values, estimate them here. For the 97.5th percentile, we do 0.975. Look at that value, 1.96. What does that look like? Does that look familiar at all? So that is the Z star multiplier that you may have seen before when making a confidence interval. Okay. All right. So yeah, we can estimate it using Monte Carlo methods. R actually allows, using integrals and calculus, R will calculate exact quantiles of distributions. So for example, you can get the exact 97.5th percentile using the Q norm function in R. So here's like Monte Carlo estimate of 97.5th percentile. And then we can get the exact value for that. So we can see the true exact value is 1.59964. So that's why we usually use 1.96. It's actually just that rounded. So let's look at a brief example here about how we can simulate values to approximate things. So as I mentioned before, the exponential and Weibull distributions can be used to model wait times. The uniform distribution can also be used to model wait times. So I plotted the beta and exponential distributions before. Let's get back to that code. Try to get back to that code. There we go. So here we have like the SpongeBob plus example. Okay, so for example, we can generate values from a uniform distribution. Let's see what parameters that takes. So the continuous uniform distribution, which we're working with here, takes a min and a max value. Okay, so for example, get rid of those parameters. If we wanted to generate 100,000 values from the uniform distribution, okay, we could use this code. Here is the uniform distribution. Okay. So you'll notice it seems like a fairly constant height. If you made it larger, actually, 100,000. It's a fairly constant height as you go across. So you have values that are bounded between two numbers, the min and the max, and then values have an equal probability falling anywhere in between there. That's the uniform distribution. So let's look at this example. So we are using an example from the show SpongeBob. So if you have seen SpongeBob before, maybe you have seen the episode where SpongeBob, this is from season 1, which came out in 1999, many years ago, over 20 years ago now. So this was a show I loved as a kid. So SpongeBob in this episode is stuck in far away from home in this town called Rock Bottom, and he's waiting for a bus. Okay. So here we're supposing SpongeBob's stuck in Rock Bottom, waiting to catch a bus to his favorite restaurant, the Krusty Krab. His bus comes every 20 minutes. Okay, so the bus route comes every 20 minutes, and let's suppose SpongeBob just showed up at the bus stop. Doesn't know when the next bus is coming. So his waiting time until the next bus comes, in this case, because the bus comes every 20 minutes, we're going to assume it's exactly on time every time, is uniformly distributed with a minimum of 0 and a maximum of 20. Okay, so let's plot this here. So uniform distribution, SpongeBob's waiting times. Okay, so minimum of 0, maximum of 20. Okay. All right. And maybe we'll even make the bars yellow in honor of SpongeBob being yellow. So we'll say fill. See, it probably doesn't look very nice. Oh my gosh, that looks awful. Maybe we'll make the color like brown. SpongeBob's pants are brown. Maybe that'll help. Okay, yeah, cool. Kind of looks like SpongeBob. All right. So here's his waiting times. Okay, 0 to 20 minutes. Let's see. So we're simulating here SpongeBob waiting for the bus 100,000 times. And here's all the different number of times, how long it took him to catch the bus at his bus stop. So we can use Monte Carlo methods here by generating or simulating him waiting for the bus to approximate his expected waiting time. In statistics, when we say expected, this means average or mean waiting time. So let's get that value. So how can we get that value? Well, let's see. Oh, we got to store this result here first. Okay, so let's call it like sponge weights. And then we can pipe it into ggplot like that. Great. Sponge weights. And then we can get the average of that by, okay, so now, so base our way to do this, I would use $, get that column value. That's the column in this data set. It's called value. So you can access that with the $, and then you could do the mean function around it. This is like the base R way of getting it. So about 10. If you wanted to do this with the tidyverse, so I'll do it both ways. Base R way. I would be personally, because when I first started learning R, I actually didn't know the tidyverse at all. And I learned it from just base R. So I still have that habit of doing it that way. If you want to do it with the tidyverse, just a little bit longer. Okay, so you would do like, you would use this pull function, which is kind of like equivalent to using the $. And then you pipe it into the mean function. This way uses pipes. This way does not. They'll both give you the same answer. So, okay, so about 10 minutes. Nearly exactly 10 minutes is SpongeBob's expected waiting time. That's what we approximate using Monte Carlo methods. What do we see that's equal to? The midpoint, exactly halfway between the minimum and the maximum value. And if you look up the uniform distribution on Wikipedia, again, this is technically called the continuous uniform because values are continuous. You could have a discrete uniform distribution. For the continuous uniform, which we're working with here, it's 1/2. The average or expected value is 1/2 of the minimum plus the maximum. Essentially the midpoint. All right. What is the median waiting time? Okay, we can approximate that. We'll use the tidyverse way here, I suppose. And then the median function. You could use the quantile function like we did last time. That's fine. So what's the median? Also really close to 10 minutes here. Yeah. So the median, yeah, if we look at the Wikipedia page, let's see. Yep, we can confirm that theoretically, if we did a large enough sample size, these will end up being nearly or pretty much equal. So 50% of the time, we expect SpongeBob to wait 10 minutes or less. On the other hand, 50% of the time, we expect SpongeBob to wait 10 minutes or more. Depends on, I guess, glass half full or half empty, however you want to look at it. Okay. Let's see. Okay, so let's further complicate this situation here. So let's suppose that SpongeBob's also waiting for his friend Patrick to first get to him at rock bottom before he catches a bus to the Krusty Krab. So SpongeBob's waiting at rock bottom. Patrick, his friend who is a starfish, is at Glove World. If you've seen this episode, you would know what I mean. Oh, and if you're curious, here's a clip I linked to here of SpongeBob waiting for the bus in this episode, so you could check that out if you wanted. So Patrick is trying to get to SpongeBob so that they can get the bus together to the Krusty Krab, okay? And these are different bus routes. So Patrick has his own bus route he's trying to catch to get to SpongeBob, and then they catch SpongeBob's bus he's waiting for to get to the Krusty Krab. Okay. So Patrick's got to get a bus from Glove World to Rock Bottom, which takes exactly 10 minutes once he's on the bus. The bus comes to him every 30 minutes. So we'll use a uniform distribution to model that, because if you showed up at a bus stop that comes every 30 minutes consistently, your waiting time will be uniformly distributed from 0 to 30 minutes. The bus might be there right away. It could be, if you just missed it, it could be up to 30 minutes until the next bus comes. But it's going to be somewhere in between 0 and 30. Okay. So let's generate Patrick's waiting times separately here to answer this question. So first, let's see. Yeah, let's get Patrick's waiting times. So we'll call this Patrick waits. And Patrick's bus comes every 30 minutes, so we'll change this to 30. Patrick is also like yellow and brown are sort of SpongeBob's colors here. And actually remembered, I just added these in. I paused the recording real quick and added these in. We can get the exact colors in our plots because it's fun. So we can use what's called hex code to match the colors exactly. So there's like a website, for example, you can like upload an image and then get the exact hex code color for it. So here's like, oh, I want the SpongeBob yellow. So you click here, and you can copy this. If you put this code in R, you can get the exact color of like SpongeBob, or like his brown or his red. It's kind of fun. So then we can use that, and this is called like hex code for the color. So I Googled like hex code color from image, and then there's online tools for that, which is kind of fun. So yeah, we can get like the exact yellow of SpongeBob here. So let's do that. And get like the exact brown of his pants. Yeah, that's kind of fun. Okay. And then run that. It looks pretty similar before. But now we could do the same thing with Patrick too. Okay, so here's like SpongeBob's waiting times. Okay, let's get it for Patrick. So Patrick, let's do his pink and green maybe. Let's see. So Patrick will make like the inside of the bars pink. And then we'll use his green maybe for the outside of the bars. Okay. All right, so just it makes it a little fun. All right, so we can do that. Ooh, that looks okay. maybe we'll do purple. We'll do his purple. Because that green doesn't look the best. Yeah, okay, that looks a little better. Okay, so we got SpongeBob's waiting times, 0 to 20. Patrick's waiting times, 0 to 30. Oh, and we'll update the title. Patrick. Okay. All right. And now, let's see. What is SpongeBob's total expected waiting time? Emphasize that. Total expected waiting time until he catches a bus back to the Krusty Krab with Patrick. Okay. So we can get this. How can we get this? So Patrick first needs to wait to catch his bus, take his bus, which takes 10 minutes to get to SpongeBob, and then SpongeBob and them need to wait and get the bus back together. So total time equals Patrick wait time plus 10 minutes for his bus plus SpongeBob bus stop wait time, because there's two different buses. Okay. Okay. Oh, you know what? Wait, let's see. How did I ask it? Oh, until he catches a bus. Okay, so we're not going to worry about the time the bus takes to get to the Krusty Krab. We're just saying in time until he's on a bus that's taking them to the Krusty Krab. So total time, and actually let's add this. Let's see. Patrick waits. Let's add this to like the sponge waits. Yeah. Let's see. Total time. Yeah, let's create a data set called like total waits. So it'll be Patrick's waiting time. We'll get it using the base R way. Plus 10 minutes plus, and then we'll call this like value. Patrick waits, total waiting time plus 10 minutes. Maybe we'll organize this all into one data set. Let's see, yeah, let's do that. So maybe we'll just call this waiting times. We'll call it like time, and then yeah, we'll just do this. Let's redo this a little bit. So updated this to called waiting times. updated the variable to time, and then we created a new variable called person. Okay, so now the data set, we're just making it a little bit tidier here. It has like, in this first simulated scenario, world number 1, SpongeBob waited 17.3 minutes for the bus. And then we'll add on like Patrick to this. Okay, so Sponge waits, we need to update that. And then the variable is time. Okay, and then Patrick will say, we'll do the same thing. Patrick's waiting time, except he's waiting 30 minutes. Person is Patrick. Yep. Okay. Maybe this is making it just more difficult, but yeah, this feels like it's making it a little bit more difficult, but let's see. We'll still sort of stick with it here. And then we got Patrick's waiting times. Okay. Okay, let's see. Maybe we'll move this down here. There's just Patrick's stuff. Okay. Bind rows. Perfect. Okay. Okay. So now this has all times, has has rows for Patrick. If you arrange, you could see that, and it also has waiting times for SpongeBob for each simulation. Let's see. What's the easiest way to get this? Gosh, maybe I was making it more complicated by doing a tidy format. You know what? Instead of bind rows, we're going to do bind calls, which binds it by the columns. Yeah. I didn't like that. Maybe we'll call this like Patrick instead of time. Oh gosh. And then for SpongeBob, we'll do it. It's getting a little messy. Maybe, yeah, let's not worry about the person variable at all. Okay. Just get rid of that person variable. We're not going to do anything with that. Okay. Patrick. Perfect. Okay. There we go. So here's this code in case you wanted to copy it to catch up here. And then this code. Okay. Now that we have this data set that has these two variables, we can get the total waiting time using mutate. This is what I was trying to get to. I really wanted to use mutate to do this. Ended up being a lot though. So total waiting time equals waiting time for Patrick plus 10 minutes to get his bus to SpongeBob plus SpongeBob's waiting time. Sometimes it takes a little extra work to get things in a tidy format. Now we can see in each simulation, here's the total time it took them to get on a bus to the Krusty Krab, to be heading towards the Krusty Krab. The sum of their two waiting times plus 10 minutes for the bus in between. So then we could plot the total waiting times. But let's just get the expected value. Yeah. Okay, so the expected value. We can do this. We'll use poll on the total, get the mean. So 35 minutes about. That makes sense given that Patrick's expected waiting time is 15 plus 10 to take the bus to SpongeBob, so that's 25. And then 25 plus SpongeBob's expected waiting time, which was 10. So 25 plus 10 is 35. That's what we get for the overall expected total waiting time. Okay. All right. What is the median total waiting time? Now we can get that using the median instead of the mean function. Great. Let's see what that looks like. Also really close to 35 minutes. Okay. The uniform distribution is a symmetric distribution. So the median is equal to the mean. And that's why we see this here. Because actually, even though this is a function, this total waiting time is equal to Patrick's waiting time, which is uniformly distributed, plus the number 10, plus SpongeBob's waiting time, also uniformly distributed. You can prove mathematically, actually, that a uniform random variable plus another uniform random variable plus a constant is equal to a uniform distributed random variable. And you could actually, yeah, you could plot this to see that that is the that's the case. We looked at the total. Oops. Object total now. Oh, we need all times instead of waiting times. Oh, weird. That does not look uniformly distributed. Huh. Oh, maybe I was wrong. Yeah, that is not a uniform random variable. It is something else. Interesting. Okay, I'm a little rusty on my math stat. It is not a uniform, but there's the distribution of the waiting times there. Okay, so let's see the quantile function. Okay, so we can get the 99th percentile for the total waiting time for SpongeBob. So how long it took him and Patrick in total to get on a bus towards the Krusty Krab. Only 1% of the time or less. So, for example, we can use the quantile function like this to estimate the 99th percentile of the standard normal distribution. one way to think about a confidence interval is as a construction of two percentiles that capture 95% of the data. So you could have the 2.5 percentile and the 97.5th percentile as cutoffs, so that you have 2.5% on the outside in each tail, leaving you 95% in the middle for your 95% confidence interval. So we'll use the quantile function and that idea to get a 95% confidence interval here for their total waiting time. Okay. Our studio server is getting a little tired. Okay. So let's see. Let's get this. So let's get the lower bound for the confidence interval and then the upper bound. So just like up here, we can do, we want to do the quantile function and then probs equals 0. So we'll get the 2.5 percentile first, and then we'll get the 97.5th percentile here. That's our upper bound for their total waiting times. And then if we run this, we can use like inline R code to say what our 95% confidence interval is. So let's do that. So we are 95% confident that SpongeBob and Patrick, or that SpongeBob in total will wait between, I haven't used inline R code in a while, but you do these single backticks on each side in the lowercase r, and then you can put R code in here. So we'll wait, and then we'll use the round function to round it to 2 decimal places. We'll wait between blank and blank minutes until him and Patrick are on a bus heading to the Krusty Krab. We'll change this one to the upper bound. Okay. And let's knit that and see where we're at. And we'll probably feel pretty good about that. Okay. So using our inline R code, you're 95% confident that SpongeBob in total will wait between 15.49 and 54.52 minutes until he, I guess I should, yeah, technically the grammar should be he and Patrick are on a bus heading to the Krusty Krab. So let's fix that grammar mistake until he, yeah. Cool. So that's how we can use inline R code. Here you can see the distribution of values, okay? So 15 minutes is about here. 54 minutes looks like somewhere around here. Okay, so the middle 95% of the data. We can use Monte Carlo methods to estimate that. Okay, but that might be a little bit of a pain to derive mathematically. Certainly could do it. It would involve some integrals. Involving this PDF function wouldn't be fun. I would much rather simulate it like we did and just get approximate values like that. Okay. So yeah, so that was how we can use, that was the last part. Yeah, that was the last part for the SpongeBob example. that's how we can use Monte Carlo methods to sample from distributions. We saw how we can sample from a vector of the names of fruits, and also sample from a vector of numbers to simulate dice rolls. Okay. So that's where we'll leave it in this video. In the next video, we'll look at how we can use Monte Carlo methods or simulation methods to conduct what's called permutation or randomization tests in R, which are a useful alternative to parametric tests like the two-sample t-test or one-way ANOVA, things like that.